My name is Timon Gehr, and I'm going to present lambda-psi exact inference for high-order probabilistic programs. This is joint work with Samuel Steffen and Martin Wetjeff. Probabilistic programs represent conditional probability distributions. For example, this program starts with a uniform buyer on the bias of a coin. The coin is then flipped 10 times, and we observe the number of times it resulted in heads is divisible by 3. We then return the bias. The program represents the posterior distribution of the coin bias given the observed evidence. We are interested in computing basic properties of probabilistic programs, such as the density of the represented conditional distribution, probabilities of events related to program outputs, or expected values of random variables depending on program outputs. The computation of such properties is called probabilistic inference. Because probabilistic programs are very expressive, inference is not directable in general. Most approaches to probabilistic inference are based on approximation. For example, distributions might be approximated by a set of samples. Probabilities and expectations might be approximated empirically and using floating point arithmetic. Different approaches make different implicit assumptions and give different guarantees. In practice, assumptions are seldomly checked automatically and often violated. Therefore, results may have to be validated, which is not always easy. However, here we are pursuing a different approach. Instead of sampling, PSI computes exact results using symbolic reasoning. So why do we care about symbolic inference? In some cases, symbolic inference is cheap, even cheaper than approximate inference approaches. When it works, you get what you asked for. When it does not work, you notice. It either does not terminate or the result is not suitably simplified. The original PSI had a number of limitations. All variables were real variables. Arrays were based on unrolling and array indices were not allowed to be random. Only procedural style code was supported. In particular, there was no support for higher order functions. PSI can answer inference queries, but PSI programs themselves cannot use this inference operator as a first-class language feature. Disintegration was not documented. We had a preliminary implementation, but our approach was rather easy to extend with disintegration, so we did not notice that it is interesting. lambda-psi addresses all of those limitations. It builds on top of PSI and adds more language features. There's actually another obvious limitation, namely PSI only supports statically bounded loops, but we leave this for future work. lambda-psi adds support for first-class functions with polymorphism. For example, we can express the initial example like this. The higher-order function fill creates an array containing the results of 10 coin flips. We then observe that the sum of the elements of this array is divisible by 3. In particular, functions with possibly random behavior can be manipulated as first-class values. Functions themselves can also be random. Here we create a random function, but that function has deterministic behavior. In general, functions can both be random and have random behavior at the same time. Now, how does lambda-psi perform exact symbolic inference? In the source language, randomness is implicit. The program reads like a simulation. Therefore, we translate the program to an intermediate representation that explicitly tracks randomness. Note that our intermediate language uses some non-standard notation that we can more conveniently manipulate than measure-theoretic notation. Our notation is pointwise, so we don't have to explicitly track measurable sets. For example, we use Dirac deltas to represent deterministic relationships. For example, here, x is deterministically 0. For continuous distributions, we use the Lebesgue measure. Here we scale it so it represents a uniform distribution on an interval. Discrete distributions are represented as linear combinations of Dirac deltas. For example, here, z is 1 with probability y and 0 with probability 1 minus y. Multiple such probabilistic assignments can be combined via multiplication. As we return z, we have to marginalize x and y. This is expressed using integration. Marginalizing a Dirac delta amounts to substitution, as illustrated in this generic rule. To marginalize x, lambda-psi automatically applies this rule and also performs basic algebraic simplifications. To marginalize y, we integrate the terms y and 1 minus y from 0 to 1. Each integral is equal to 1/2. This way, we get a simplified term representing the same distribution as the original program. lambda-psi automates this kind of reasoning. To represent first-class functions as well as first-class distributions, we introduce two kinds of lambda expressions. Lowercase lambda functions are standard. Uppercase lambdas abstract over distributions. This example program represents a function f with random behavior, but f itself is a deterministic value. The function takes a parameter x and returns the distribution over a return value set. This distribution is then specified in the way we have already seen. The temporary variable y represents the return value of the call to uniform. The distribution returned by a function is not necessarily normalized, as observations simply remove all probability weight corresponding to bad executions. We can also represent functions that are themselves random. Here we specify a joint distribution of x and f, where f captures x, with a marginalized variable x. As we have seen, distributions can be easily represented as first-class values in the intermediate language, and this capability is exposed to the source language. Values of type distribution represent probability distributions. In other words, they are normalized. In this example, we compute the expected value of a geometric distribution with parameter 1/3 and sample a single value from it. This can be represented in the intermediate language like this. We define the geometric distribution with a capitalized lambda expression and a sum over integers, and then bind it to the variable g using a Dirac delta. The expected value is computed using the standard formula. To sample a value s from g, we simply use the distributional application. λPSI is an operator for using inference within a program. It takes a function with 0 arguments and returns the distribution over its outputs. Importantly, infer normalizes this distribution. This way, the infer operator supports nested inference queries. For example, this can be used to create a model of rational agents that themselves use probabilistic inference. Note that in this program there are two observations. Due to the way infer normalizes its result, it essentially creates a dynamic scope for observations. The first observation only influences the distribution of y within the nested inference context. In other words, the distribution d will simply be the uniform distribution on the interval between x and 1, while x remains uniformly distributed between 0 and 1. The implementation of symbolic nested inference is rather simple. Nested inference just calls the representation of the function to obtain the corresponding distribution and normalizes it by scaling it by the inverse of the total weight in that distribution. I will now discuss an equation that is particularly important for some of our simplification rules. Our goal is to rewrite a deterministic dependency of a variable y on a continuous variable x such that y becomes manifestly continuous and the variable x can be marginalized using substitution. We require f to be differentiable. If we additionally require that the derivative of f is not 0, the equation can be simplified. Essentially, we just enumerate the values where f of x is equal to y and rescale them appropriately. Intuitively, values of y are less likely in regions where f changes rapidly. This can be formally justified using the substitution rule of Lebesgue integration. For example, the following integral was shown earlier. We will now simplify it using our rule. We can instantiate the rule for a product of Lebesgue measure and Dirac delta to reverse the deterministic dependency between y and z. In this case, the derivative is simply 1. Furthermore, the equation has a single solution. λPSI also supports continuous observations. cobserve observes that the first argument, which is expected to have a density, is equal to the second argument. This is an observation of an event with probability 0. Simple cases like this observation with continuous noise can be implemented by a rescaling of the posterior distribution. This is typically supported by probabilistic programming systems. However, λPSI also supports continuous observations where neither of the arguments is directly sampled. This is not commonly supported. The only system of which we are aware that can handle this is Hakaru. However, in contrast to λPSI, in Hakaru, this kind of observation cannot be represented as a term. Rather, it is implemented as a transformation of Hakaru terms. How does this work? Use the following rule. Here, the double slash stands for disintegration, which is a generalization of division to measures. Essentially, this allows us to get an expression for the density of x. cObserve is based on disintegration. For the example on the left, it fixes the value of z to the observed value 0, weighting the distribution by z's density. The result is an unnormalized distribution, which we later have to normalize in order to perform inference. Note that we cannot directly apply our disintegration rule, because in the numerator, z is generated by a Dirac delta instead of a Lebesgue measure. We can fix this by rewriting the expression using the linearization rule. In general, we may have to perform this step multiple times. Here, one such rewrite is sufficient and we can apply the disintegration rule. After a few more simplification steps, we are left with the following result. The total weight of this distribution is 1/2, therefore we can normalize it by multiplying by 2. The resulting marginal distribution of x is uniform between 0 and 1/2. For the example on the right, we follow the same process. Here we have to be careful to correctly apply the linearization rule. The partial derivative of y divided by x with respect to y is 1 over x. Therefore, we have to multiply the right-hand side by the absolute value of x. After simplification, we get this result. The total weight of this distribution is 1/8. Therefore, we can normalize it by multiplying by 8. The resulting marginal distribution of x is triangular with density increasing from 0 to 4 between 0 and 1/2. Note that we get different results even though in both cases we observe that y is 2 times x. This is called the Borel paradox, and it is the reason why cObserve has 2 parameters in contrast to observe, which only takes one Boolean argument. Note that because our linearization rule is quite general, lambda-psi supports this integration for some first-order programs that Hacker can express but cannot disintegrate. I would like to conclude with a few plots from our paper that illustrate some things that lambda-psi can do. These plots show results from a nested inference example taken from probabilistic models of cognition by Goodman and Tenenbaum, who only compute the approximate marginals. Here we have computed full joint posteriors, both using the original rejection sampling method and with lambda-psi. While the approximate results each take more than 10 minutes to sample and generate tens of megabytes of data, the exact lambda-psi results are computed in a couple of seconds each and are represented as a succinct symbolic expression. This Bayesian linear regression example demonstrates one of the major benefits of symbolic inference. We can have symbolic parameters and perform inference for an unbounded number of queries at once. Here we symbolically compute the marginal posterior of the function f at each possible value x. This kind of parallelism is also one of the reasons why symbolic inference works well for nested inference queries. Thank you for listening. The source code of our implementation of lambda-psi is hosted on GitHub.